A turbocharger is a relatively simple device with few moving parts. Turbochargers are used primarily to improve engine performance, and when used are very important to proper engine operation. In this program, we'll review the turbocharger, how it operates, its parts, and the function of each part. Failure modes analysis procedures will be reviewed as applied to the turbocharger alone and as part of a complete engine failure modes analysis. The emphasis in this program is effective diagnostic procedures for turbochargers and engine problems that are closely related to turbocharger failure. A turbocharger has three basic sections: the compressor wheel and housing, the turbine wheel and housing, and the center housing. The turbocharger takes in filtered air for the engine on the compressor side. Exhaust gases go out through the turbocharger on the turbine side, causing the turbine wheel to rotate. This provides power for the turbocharger to compress the filtered air supplied to the engine. The filtered air is drawn into the turbocharger, compressed, and forced into the engine cylinders under pressure, supplying a greater mass of air for combustion. If fuel flow to the engine is also increased, power output from the engine will increase. All of the parts of the turbocharger are precision components, and they are manufactured to very close tolerances. Because of the high speeds and the heat and pressure of turbocharger operation, the bearings and shaft ride on an oil film. Clearance is built into the internal components to ensure that this oil film is maintained. A slight amount of play in the shaft that runs through the turbocharger is one sign of this clearance, which is necessary to assure proper functioning of the unit. Shaft speeds can exceed 100,000 RPM during operation. Lubrication of these rotating parts is critical to proper operation. To assure proper lubrication, filtered engine oil is supplied at normal operating pressure by the engine. This brief review is intended to provide a basic understanding of turbocharger operation. The background information will be valuable in your diagnosis and repair of a customer's turbocharger failure. To diagnose specifically why a failure occurred and what type of repair is needed, failure modes analysis is used. The cause of the failure is traced and corrected. Failure modes analysis is critical on turbochargers because the results may indicate that a complete engine failure modes analysis is required to find and correct the cause of the turbocharger failure. Often, failure modes analysis will show that the turbocharger has not failed. Proper diagnosis of a non-failed turbocharger is important for two reasons. First, identification of a non-failed turbocharger will lead to further investigation and repair of the cause of a performance complaint. Second, proper diagnosis eliminates the unnecessary expense incurred when a non-failed turbocharger is replaced. The 7-step failure modes analysis procedure is recommended to assure that the cause of a failure is properly identified. The 7 steps of the procedure are: identify the customer's problem, consider all the symptoms, evaluate the operating environment, research the machine's history, examine and disassemble the machine, determine both primary and secondary failures, consult support materials. Use of this procedure will assure correct repair of a problem and eliminate unnecessary expenses. The key to proper failure analysis is to know when a turbocharger has failed and when it has not. There are 5 basic engine-related symptoms that indicate a potential turbocharger failure: loss of power, excessive smoke, excessive oil consumption, excessive noise, and oil leakage. A closer look at these symptoms will provide some additional direction for planning the analysis. There are many possible engine-related causes for a loss of power. It can occur gradually over a period of time, or may occur quite suddenly. Generally, diagnosis of loss of power complaints requires analysis of the complete engine. Excessive smoke has 4 likely causes: lack of sufficient air to the engine, overfueling of the engine, excessive internal engine wear, or injection system problems. The only cause related to the turbocharger is insufficient air, which can be caused by a plugged air cleaner or restrictions in the intake or exhaust system. Excessive oil consumption can result from numerous causes besides the turbocharger. A complete diagnosis is required to be sure that you have determined the source of the problem. Some noise results from normal turbocharger operation. Excessive noise can result from air manifold leaks or wheel rub within the turbocharger. If it is turbocharger wheel rub, a complete failure analysis is required. The final engine-related symptom that may indicate a turbocharger problem is oil leakage. This can result from a turbocharger failure or operating conditions, such as long idle periods or light loads. An engine problem may also result in oil leakage from the turbocharger. These engine symptoms indicate potential turbocharger failures. Other factors can also contribute to these problems and may be the cause of a problem. A thorough analysis will isolate the problem and its cause. Turbochargers will run indefinitely if provided with filtered air, an adequate supply of lubricating oil, and normal engine exhaust temperatures. They are very sensitive to variations in these three conditions. There are 5 basic causes of turbocharger failure: lack of lubrication, contaminated lubrication, foreign object damage, excessive temperatures, and manufacturing defects. Identification of the cause of a failure helps in determining the correct repair procedure and will prevent repeated failures and keep customer downtime to a minimum. Lack of lubrication is one of the main causes of turbocharger failure. The resulting damage to the bearings and shaft often causes wheel rub in the turbocharger. An adequate supply of clean lubricating oil is critical to performance. An engine problem that interrupts the oil supply can damage the turbocharger. Frequent engine shutdowns without a cool-down period can also damage the turbocharger. Placing the engine under load without proper warm-up can also cause damage. Contaminated lubricating oil can also cause a failure. Abrasive particles in the oil will cause excessive wear within the turbocharger, resulting in the wheels contacting the housing. Contamination can result from defective or plugged oil filters, improper oil change intervals, or a debris-generating engine failure. Foreign object damage will cause an imbalance of the turbocharger rotating parts. Any nuts, bolts, or similar debris left in the intake system will damage the turbocharger compressor wheel. If the intake system is defective, dirt entering the system can damage the turbo. A valve failure, or a similar internal engine failure, can cause foreign object damage to the turbine wheel. Excessive engine exhaust temperatures are another cause of turbocharger failure. The most common cause of excessive exhaust temperature is overfueling of the engine. Exhaust temperatures rise when the engine is overfueled, and the turbocharger will overheat, causing the turbine housing to erode. Turbine speed also increases with exhaust temperature, putting more stress on the entire turbocharger. Manufacturing defects can also cause a turbocharger failure. These are usually low-hour failures and are relatively rare. A thorough diagnosis will identify these failures as well as those caused by the other problems. An in-depth examination of typical failed turbocharger parts is next. This examination will be divided into 3 parts. Each part will deal with one section of the turbocharger: the compressor wheel and housing, the turbine wheel and housing, and the center housing. 3 basic failures are associated with the compressor wheel and housing assembly. Foreign object damage is a primary failure mode and is easily identified. Any damage to the fins, even small nicks, will result in an unbalanced turbocharger and eventual failure. Wheel contact with the housing is the second failure mode. This secondary failure occurs because of a bearing failure, an out-of-balance failure, or other similar failure that results in excessive shaft movement. The third failure mode is oil in the housing. This is also a secondary failure. If the seals are defective, oil can enter the housing. If the air cleaner is restricted, the turbocharger will draw oil from the center housing. If the engine crankcase vent or oil return becomes restricted, Oil can also be forced by the seals. Failure analysis will isolate the problem. The turbine wheel and housing are affected by 4 failure modes. Foreign object damage is one mode. This type of failure occurs if nuts, bolts, or similar debris is left in the exhaust manifold. A foreign object failure can also indicate an engine valve failure or a similar debris-generating internal engine failure. Turbine wheel contact with the housing is also a turbine side failure mode. Like the compressor wheel, this is a secondary failure. Any problem which causes excessive shaft movement, such as a bearing failure or shaft imbalance, will cause wheel contact. A close check is important. A third turbine side failure is erosion of the turbine housing. Erosion results from prolonged periods of high temperature operation and reduces turbocharger efficiency. Erosion can also cause foreign object damage to the turbine wheel. Oil in the turbine housing is the 4th failure mode. Because of the high exhaust temperatures, this may appear as carbon buildup. This type of failure can result from certain operating conditions. If the engine is idled for long periods or operated under light loads, unburned fuel can be expelled from the engine. The appearance of the fuel as it slobbers out of the turbocharger is similar to an oil leak. This condition should clear up when the engine is placed under load. Other potential causes include a restricted turbocharger oil return line or a crankcase vent. This increases the pressure within the turbocharger, which can force oil by the seals. Be sure to trace these problems and correct them, or they may cause repeat failures. An engine problem can also feed oil into the turbine housing. If the inlet to the turbine housing and the exhaust manifold are wet with oil, then a problem exists in the engine. Several failure modes are associated with the center housing and the parts inside the housing. Lubrication-related problems affect the bearings and shaft. Lack of lubrication results in extensive damage to bearings and the shaft. Contaminated lubrication will result in excessive wear on the bearings and shaft. Both lack of lubrication and contaminated lubrication failures initially show up as wheel rub problems. Excessive exhaust temperatures can discolor and damage the shaft and bearings, resulting in wheel rub. Oil passages can become plugged by coking oil under excessive exhaust temperature conditions. Seal failures in the center housing are often secondary in nature. Seals can take a set and fail when exposed to excessive temperatures. Bearing wear and shaft movement also create seal problems. The last cause of turbocharger failure, a manufacturing defect, is quite rare. As noted earlier, manufacturing defects usually cause low-hour failures. The more common manufacturing defects are undrilled oil passages and porous center housing castings. Seal failures due to improper assembly have been identified as well. Proper failure modes analysis of the turbocharger makes use of a systematic procedure that will determine the condition of the unit. This procedure will help to identify when a turbocharger has failed and why it failed. It is also important to identify turbochargers that have not failed. By systematically analyzing the turbocharger, the correct failure mode can be identified and the primary cause of the failure can be corrected. This analysis takes very little time and it assures that all the likely causes of a problem are covered. The diagnostic system for turbochargers uses a 2-phase approach. The first phase is the 7-step visual check of the turbocharger. This visual check will verify the condition of the unit and will identify the potential cause of most failures. The second phase is checking the turbocharger bearing end play and radial play. Check your results against the appropriate technical manual. The 7 visual inspections are the compressor housing inlet, compressor housing outlet, turbine housing inlet, turbine housing outlet, center housing casting and connecting joints, center housing interior, shaft rotation and clearance. This brief, comprehensive inspection will provide direction in determining the failure modes and repairing any problems. To facilitate the inspection, an inspection chart can be used that lists the inspection steps in the proper order and shows potential failure modes for each step. Check off each step as you complete the inspection and note any problems. The first inspection is the turbocharger compressor inlet. The most obvious failure here will be foreign object damage. Foreign object damage may be extensive or very minor. In either case, the source of the foreign object must be found. So mark this on your checklist before you continue the inspection. The second compressor inlet check is wheel rub on the housing. You'll need a good light for this check. Look very closely for any score marks on the housing itself and check the tips of the compressor wheel blades for damage. The second inspection is the compressor housing outlet. The outlet should be clean and no oil or dirt should be present. Mark it on your checklist if oil or dirt is found. Steps 3 and 4 of the inspection involve the turbine end of the turbocharger. Step 3 is checking the turbine housing inlet. This is where exhaust gases enter the turbine housing. The center dividing wall provides a steady flow of gases to the turbine wheel. It must be in good condition. A light coat of carbon is normal. Cracking or missing pieces indicate excessive exhaust temperatures. If the inlet is wet with oil or has excessive carbon deposits, an engine problem is likely. Record defects on your checklist. Step 4 of the inspection is the turbine housing outlet. Use a flashlight to look up inside the housing and closely examine the turbine blade tips. Damaged blades indicate foreign object damage has occurred. Note any damage on your checklist because inspection of the engine will be required. Inspect the wheel blades and housing for evidence of wheel rub. Wheel rub can bend the tips of the blades with the housing showing wear or damage. Note any oil or excessive carbon buildup on your list. The center housing assembly is inspected in steps 5 and 6 of the turbocharger inspection procedure. Both the outside and inside of the center housing should be checked. Step 5 is a visual inspection of the outside of the center housing. All connections to the compressor and turbine housing should be checked at this time also. If oil is present, make sure it is not coming from a leak at the oil supply or return line. Internal inspection of the center housing is step 6. To perform this inspection, you will need a flashlight. Look through the oil return hole to check the condition of the shaft and/or bearings. There should not be excessive carbon deposits on the shaft or in the housing. Excessive bluing along the complete length of the shaft indicates a possible lack of lubrication caused by an engine failure or improper operation, such as hot shutdowns. The final step in the turbocharger inspection procedure will provide information about shaft rotation and clearance. Mount the turbocharger in a vise and check shaft rotation and clearance. First, rotate the shaft. It should turn freely. There may be some drag, but the shaft should not turn hard. Next, pull up on the compressor wheel end of the shaft and press down on the turbine end of the shaft while rotating the shaft. The wheel should not contact the housing at any point. There will be some play because the bearings inside are free-floating. Check shaft end play by moving the shaft back and forth while rotating it. There will be some end play, but not to the extent that the wheels contact the housings. The second phase of the diagnostic procedure involves checking bearing radial play and end play with a dial indicator. This procedure is not required if a failure mode has already been identified. These tests provide measured information on the condition of the turbocharger, which is then compared against established standards. Both of these tests are outlined in the appropriate technical manual. Proper specifications are also provided. These diagnostic procedures will allow you to determine the condition of the turbocharger. If the turbocharger has failed, analysis of your inspection notes should direct you to specific areas of the engine to correct the problems causing the turbocharger failure. It is not unusual to find that a turbocharger has not failed. If your turbocharger passes all the inspections, the problem lies somewhere else. Identification of primary and secondary failure modes is an important part of turbocharger failure analysis. Often the turbocharger failure is secondary, and the primary failure mode is in the engine. Identification and repair of the primary engine failure is critical. The following guidelines will help determine the engine repairs that are required based on your turbocharger inspection. Specific repair procedures are covered in the appropriate technical manual. Lack of lubrication failures result from engine problems or improper engine operation. If the turbocharger inspection shows a lack of lubrication failure, the engine should be checked to determine the cause of the loss of lubrication. If you determine that operation is the problem, discuss proper procedures with the customer. Contaminated lubrication failures require inspection of the engine. Often oil contaminants are a sign of an undiscovered engine failure. Extensive repair may be required. Foreign object damage to the compressor wheel requires extensive inspection of the air intake system. Often the foreign object is ejected back into the intake system. If it is not found and removed, it will fail a replacement turbocharger. Foreign object damage to the compressor wheel also requires inspection of the intake manifold. If the engine is not intercooled and a foreign object has passed through the intake system, the cylinder head should be removed for inspection of the engine. If the engine is intercooled, the top of the intercooler core should be inspected. Debris will collect here, but generally will not enter the engine. Turbine wheel foreign object damage may also require an engine check. The foreign object must either be a nut, bolt, or other object left in the exhaust manifold or generated by an internal engine failure. The necessary repairs must be made. Excessive exhaust temperatures result from overfueling. The fuel injection system should be checked to be sure it is performing within specifications. Proper use of the turbocharger failure analysis will identify all failures. Remember that it is very important to check for engine-related problems. There are many types of engine failures, such as bearing failures or valve failures, that make it necessary to inspect the turbocharger. Even though a turbocharger failure may not be reported, these engine failures require a thorough turbocharger inspection. That completes our review of turbocharger design, operation, and failure modes analysis. Before you replace a turbocharger, complete the full 7-step diagnostic procedure. Trace the source of the problem, the underlying cause of a turbocharger failure, and be sure to correct the underlying problem before replacing the turbocharger. Provide your customer the best service and operation possible. With an adequate supply of filtered air and filtered lubrication, a turbocharger will provide that customer with excellent performance for a long time.